All right, guys, welcome to my crash course on x86-64 assembly. Now, as you might have known if you've been following the channel recently, I've been diving into some of this reverse engineering stuff. It's pretty exciting. My goal is to start doing some IoT hacking and hardware hacking, right? Start exploring that. But before that, I'm going to do some crack me's challenges like that. And this is something that I've known for a while, but I recently refreshed my memory on it, doing all this stuff. And I think that a guide like this is definitely going to be helpful because I wish I had it when I started out. I had to kind of find other resources and paid resources and things like that to try to get all the information in one place. Like across a bunch of areas, I found this information. But when I first started out, I didn't know, hey, what really is the difference between x86 assembly and x86-64 assembly? Obviously, I knew that x86-64 was for 64-bit and x86 by itself was just for 32-bit. I knew that, but what I didn't know was like, okay, how exactly are they different as far as the syntax, right? So I'm going to show you here, these are the general purpose registers. So in addition to these, there are also two very important ones to note. So you have RIP, which is the instruction pointer. And basically what that is it's a register that tells the CPU which instruction to execute next. And then in addition to that, you have R flags, which is basically just for comparison and conditional branches, things like that, right? Other than that, all these other registers here, while they do have special names associated with them, those names don't really matter anymore because nowadays they're just used as general purpose. So meaning the CPU will use it anytime it needs storage, kind of arbitrarily. There's no special meaning to them really for the most part. But there are two that, even though they're listed as general purpose registers, generally they are used for a special purpose. But they don't have to be, right? They can be general purpose. That is RBP and RSP. So RBP is the base pointer. So the bottom of the stack, the start of the stack. And then the stack pointer points to the top of the stack. We'll talk about the stack in a minute if you don't know what that means. First, I guess I should take a step back and explain what are registers to begin with, right? Registers are basically just storage containers for the CPU to use. So a lot of, a big amount of the data is going to be moved to the RAM and stored on the RAM while the process is executing. But the CPU will actually grab some of that memory from the RAM and store it in the registers when it needs it immediately available to use it. And that just speeds up the execution speed of your CPU because it can access its basically local storage through these registers when it is working on a process, right? So when it comes to 64-bit and 32, just to go back to that, right? There's 32-bit registers and there's 64-bit registers. Now, basically, before 64-bit came around, there was x86, 32-bit, right? And what that mean was all these registers here can only store 32 bits of data. Nowadays, we've expanded that to 64-bit, right? And so because of that, these 64-bit registers, you can also still use the 32-bit registers. Now, you might have noticed this before, that this R here, that's for the 64-bit registers. If I wanted to write the 32-bit register equivalent of this, it would just be E, right? So EAX, EBX, ECX, and so on, right? So I can actually still call those 32-bit registers in 64-bit and use them, and it's basically just half the register, right? 32 is half of 64, right? So the inverse of that is not true. So with x86, I cannot use any 64-bit registers because, well, there's not enough space. It only can hold 32 bits, right? So that's a distinction that I'd like to really put up front in this video. So with that being said, right, and we understand the registers now. These are some additional registers that the CPU can use if it needs them. Let's just move on to the instructions now. So there's a number of instructions that you can use. There's a lot of different ones. And if you've ever seen assembly code before, probably seen things like move, push, pop. These are very common instructions, right? So move, you move from a source to a destination. Now here is the caveat. This is assuming the ugly AT&T syntax. And now from my experience, when you're first starting out with your reverse engineering and things like that, you're typically going to be dealing with Intel syntax, which in my opinion is a little easier on the eyes. And it's actually the opposite of this. And I'll show you that in a minute. I'll show you the comparisons after we get through the instructions here. But basically it's move and it's destination and then source. But so ignore this for now. But yeah, you can move one source, move a source into a destination. So move a value into a register, move the value of one register into another register, right? You can push things onto the stack, pop them off the stack as well. And like I said, we'll get to stack in just a second. You can increment, decrement, negate things, do a bitwise complement, right? There's a ton of different operations. You can do add, subtract, XOR stuff, OR stuff, and stuff. And, compare if you want to check for a conditional, right? If a value is less than 5 or something like that, you can use a compare function for that. And then to actually do control flow, right? So after you compare stuff, you might want to jump to a particular label, right? You can jump to a specific address or whatever, right? So jump if it's equal, jump if it's 0, jump not equal, jump not 0, and so on and so forth, right? Jump less than, jump greater than. And then call. You can do system calls. You can call return addresses. Leave, you call right before you return. You pop the address from the stack and then jump there. So this is actually a two-step thing in one instruction. You're both popping the address from the stack and then jumping to the address. So those are the ones that I highlighted are the most common instructions you're going to see. But you always have resources you can look at if you need to reference something you're not sure of. But yeah, those are the most common ones. So now for actually, explaining the stack. What is the stack, right? So, the data can be either stored on the stack or on the heap. Now, when it comes to most of this stuff that we're dealing with here, we're going to be dealing with the stack, right? So when data is stored on the stack, it's first in, last out. So the analogy that people often use is plates, right? So if you imagine in your cupboard stacking up plates, right? The last plate that you put in will be the first one that you take out, right? Because it's at the top, right? So that's kind of how the stack works. Is the first thing in is the last thing out, right? Because you're typically not going to grab the very bottom plate, right? You have to lift it up and grab it, right? So you're just going to grab from the top of the stack. And that makes things really efficient, really quick, right? You can quickly put things onto the stack, take them off, and you don't have to look and see where is the plate, right? Because you're just going to grab the top one in the stack. And so the heap, just to touch on this for a second, it's not first in, last out. It's actually just kind of unordered. There's the memory blocks off chunks of data. And the heap is typically for data of unknown size. Like for example, a string, you could have one word, you could have a paragraph, you could have, a few sentences, whatever, right? And so it's going to just allocate a certain space in memory and it's going to have an address that references it. And on the stack, it's going to have basically a link to that address in memory on the heap. So that's just the difference there. But focusing back on the stack, first in, last out. And the other caveat to the stack that can be confusing to a lot of newcomers is, we do the plate analogy, but in reality, the stack actually grows downward. So the base pointer is actually the highest address in memory, and the stack pointer, which points to the top of the stack, is actually going to grow down. So each time you're pushing things onto the stack pointer is moving down. The base stays where it's at. The stack pointer, say it's right here, you push a variable onto the stack, now it's down here. You push another variable, now it's down here. You pop one off the stack, now it comes up here. So it's actually growing from a higher address in memory down to a lower address in memory. So if you can picture, a cupboard where the plates are taped together and they're suspended from the wall, and that's really what it looks like, right? In reality, because it's growing downward. So just an important distinction to make there. Now, as far as Intel versus AT&T syntax, I'll show you what the some instructions look like in the AT&T syntax. Honestly, I'm not the biggest fan, if you couldn't tell. But yeah, it'll look something like this, right? Like this stuff here. You'll have a lot of percent signs and things like that, and parentheses and stuff like this can look kind of crazy, right? So now let's move over to the difference between Intel and AT&T syntax, just to further expand on that. Now, I apologize for this website looking kind of ugly, but yeah, this is what we're gonna have to deal with. Now, this question mark stuff, I don't know what was going on this site when it showed that, but pretend they're not there. This basically wouldn't be here. Maybe it was trying to render some character or something, I don't know. But typically, you just look something like this: move EAX, 1. And basically what that means is move the value of 1 into the EAX register. Now, with the percent sign here and the $1, this is, AT&T, it's reversing it, right? So move 1 into EAX. They both mean the same thing, but it's different ordering. So with Intel syntax, which is what I typically have worked with, it is the destination and then the source. And then AT&T, it's the source and the destination. So AT&T also requires these kind of special characters here. So you have to use the $sign when you're talking about a value, and a percent sign when you're talking about like a register or something like that. That's what I've gathered. With Intel, you don't need to specify that. It'll just know. So also, like when you're talking about numbers here, in some cases, you'll need to put in hexadecimal, right? So instead here, you use the H. You can use H to move this value. So there are little subtle differences here, right? So yeah, it even says, hey, destination source versus source destination. And even if you look at some more complex things, right, like we saw the commas earlier in the AT&T syntax, and that can look really kind of arcane. But basically what it is like we're just adding 3 to the EBX register and then moving EBX plus 3 into EAX, right? So the way you would write that in Intel, and also in Intel, it's not move, it's actually move L, apparently. I don't typically work with this, but there will be some situations where I'll probably encounter it, and you probably will as well if you dive deep enough into reverse engineering. But basically how you would write that is the value you want to add, and then parentheses, the register that you want to add it to, and then the destination you want to move it into. So that's just a quick way to go to show you the differences in how these things are written. But I mean, and the only other thing that I'd like to touch on is that in x86 64-bit, right, there's something called the red zone. And basically what that is a 128-byte zone that is actually at the top of the stack. And it's basically able to be used by functions as scratch space. That's the purpose it serves. And there's a guarantee that the system won't mess with that area of memory, right? Now, this does not exist in 32-bit on the x86, so you know. This is something that is specific to x86-64, the red zone. So if you ever hear about that, see that, that's what that is. So this is just a crash course on x86, particularly 64-bit assembly, right? Something that I wish I knew a long time ago, because a lot of the tutorials that I found were on 32-bit, and I wasn't really sure exactly what the differences were between 64 and 32. Not really too much difference. If you know 32-bit already, it's not too much to learn the subtle differences between 64 and 32, but nowadays you're mostly going to be encountering everything 64-bit for the most part, but you might encounter some 32. But yeah, just by learning 64-bit, it's easier to start with 64 and then learn 32 in my view. So yeah, the only differences would be like, look, EAX, EBX. This is technically 32-bit stuff here, right? All this is 32-bit. If there would have been an R instead of an A, then it would be 64-bit. But we could still do this. All these operations would be valid on a 64-bit system for the reasons I mentioned, right? Because it's 64, so we have access to 32. We have access to 16 even, right? And so that's just something that I wanted to point out. So hopefully this video helped you guys. If you're interested in more reverse engineering type of content, I would love to make that, but I want to make sure that this is something that you guys would be interested in. So drop a comment below and let me know if that's the case. And if you are eager to learn some more security information content, go ahead and check out the videos on screen now. I'll see you guys right over there. Thanks for watching.